Water should be a gas at room temperature. Not a little bit, not as a technicality, as a fact of physics. If you took the rules that govern every other molecule of similar size and weight and applied them honestly to H2O, you would get a boiling point somewhere around -40, -80 degrees Celsius, depending on which family of molecules you use for comparison. And what that means is that on any ordinary day, in any city on Earth, you should be breathing water vapor instead of drinking water. The oceans should not exist. Rain should not exist. You should not exist. The fact that you are sitting there right now, alive, watching something on a screen, with blood moving through your veins, and an ocean covering 70% of the planet outside your window. Every single part of that depends on an anomaly, a physical violation, a thing that water does that it simply should not be able to do by any clean and simple reading of the rules. And what Feynman taught about where that anomaly comes from dismantles any familiarity you thought you had with the most common substance in your life. The problem with water is that it is too familiar, and Feynman spent a remarkable portion of his intellectual life identifying familiarity as one of the most dangerous obstacles to real scientific thinking, because familiarity creates the illusion of understanding. You know the formula is H2O. You know it freezes at 0 and boils at 100. You know it covers most of the planet. And that collection of facts you absorbed somewhere in school produces a feeling, a very specific and very misleading feeling, that water is a solved substance, a thing understood, a thing about which there are no more interesting questions to ask. And that feeling is precisely what Feynman spent a career dismantling. Because what physics actually reveals when you examine water with rigor is not a simple substance that school summarized well. It is a substance with a set of anomalies so systematic, so interconnected, so mutually reinforcing, that physicists still debate the molecular mechanisms behind some of them. And I want to take you through those anomalies the way Feynman took his students through them. Not as a list of curiosities, as a chain of consequences. Because when you see them as a chain, when you see that all of these impossible properties have the same origin, you arrive at something that is much more disturbing than any individual fact. You arrive at the understanding that the most familiar substance in your life is also one of the most extraordinary things that exists. Let us start with the boiling point, because that is where the strangeness becomes impossible to ignore once you see the comparison. Oxygen belongs to a family of elements in the periodic table, a group called Group 16. Below oxygen in that family you have sulfur, selenium, and tellurium, and each of them forms a compound with hydrogen, just the way oxygen does. Sulfur gives you hydrogen sulfide, which is the gas that smells like rotten eggs. Selenium gives you hydrogen selenide. Tellurium gives you hydrogen telluride. Now, there is a pattern in these compounds. Hydrogen telluride boils at -2 degrees. Hydrogen selenide boils at -41 degrees. Hydrogen sulfide boils at -60 degrees. Do you see what is happening? As the molecules get lighter and smaller, the boiling point drops. The pattern is clean and consistent, and it makes perfect chemical sense. Heavier molecules have more electrons. More electrons means stronger attractive forces between molecules. Stronger attractive forces means you need more energy to pull them apart. You need higher temperature to boil them. The pattern goes in one direction, and it does not waver. Now take that pattern and extrapolate it to the lightest member of the family, the one with the fewest electrons, the lowest molecular weight. The one you would predict should have the lowest boiling point of all. You get a predicted boiling point somewhere around -80 degrees Celsius, maybe -70, depending on how you draw the extrapolation. That is what water should boil at. That is where the pattern says water belongs. Water boils at 100 degrees, not -80, 100. The gap between where the pattern says water should be and where water actually is roughly 180 degrees. That is not a small experimental error. That is not a rounding issue. That is the difference between a substance that would not exist as a liquid anywhere on the surface of the earth and the substance that covers 70% of it. And if you told a chemist from another planet who had studied every other molecule in the universe, but had never encountered H2O, if you told that chemist that this small 3-atom molecule boils at 100 degrees, that chemist would tell you that is impossible, and they would be completely right to be shocked. So what is water doing? What is the physical mechanism that drags the boiling point from minus 80 to 100? This is where Feynman would stop and say, the right question is not what, but why. What does the mechanism look like at the level where atoms actually live, where charges actually interact, where forces are actually real? And the answer begins with the geometry of the molecule itself. A water molecule is not a straight line. It is not an oxygen atom in the middle with 2 hydrogen atoms pointing in exactly opposite directions on either side. If it were, the molecule would be electrically symmetric. The positive charge from the hydrogens would cancel out perfectly with the negative charge of the oxygen, and you would have a neutral molecule with no electrical preference for any direction. But water is not shaped like that. The 2 hydrogen atoms attach to the oxygen at an angle of roughly 104 degrees. Not 180, 104. And that angle changes everything, because oxygen is an element that is extraordinarily greedy with electrons. Chemists call this electronegativity, and oxygen has one of the highest electronegativities of any element. What it means in physical terms is that when oxygen shares electrons with hydrogen in a chemical bond, it does not share equally. It pulls the electron cloud toward itself. It hoards the electrons. The hydrogen ends of the molecule are left slightly positive because the electrons have migrated away from them. The oxygen end of the molecule is slightly negative because the electrons are crowded there. And because of that 104-degree angle, because the 2 positive hydrogens are not pointing in opposite directions, but are both angled to the same side, the 2 positive poles do not cancel each other out. The molecule has a permanent electrical imbalance, a permanent dipole. One end is always slightly negative. The other end is always slightly positive. The molecule is like a tiny bar magnet that can never be turned off. And now, when you put billions of these molecules next to each other in a liquid, something happens that goes far beyond ordinary attraction between polar molecules. The slightly positive hydrogen of one molecule is drawn toward the slightly negative oxygen of a neighboring molecule. And that attraction between the exposed proton of a hydrogen and the electron-rich region of a neighboring oxygen is what physicists call a hydrogen bond. And the critical word there is bond, because while a hydrogen bond is much weaker than a true chemical bond where electrons are shared or transferred, it is 5 to 10 times stronger than the ordinary van der Waals forces that hold together other liquids of similar size. It is dramatically, disproportionately, unreasonably strong for what it is. And here is the thing that makes water different from everything else. Each water molecule can form not 1 hydrogen bond, not 2, up to 4 simultaneously, 2 through its hydrogen atoms acting as donors, connecting to the oxygen of neighboring molecules, 2 through the lone pairs of electrons on its oxygen acting as acceptors, connecting to the hydrogens of other neighbors, 4 connections per molecule, 4 hands reaching out in 4 directions, and each of those neighbors is doing the same thing, reaching out in 4 directions to their neighbors, who reach out to their neighbors, until you have an entire liquid threaded through with a vast, constantly shifting, 3-dimensional web of hydrogen bonds. In most liquids, the molecules are held together by weak forces, and they move around almost independently. They are like people in a room who are vaguely aware of each other but not really connected. In water, everyone is holding hands with 4 other people at all times. The whole room is connected. And if you want to pull 1 molecule out of that liquid, out of the network, you cannot just grab it and go. You have to break 4 hydrogen bonds first. And as soon as one breaks, the freed hydrogen tries to grab onto another neighbor. The network keeps reforming. It fights you every time you try to separate it. It takes enormous energy to vaporize water, far more than it takes to vaporize anything of comparable size. And that is why the boiling point is at 100 degrees instead of -80. You are not just overcoming weak intermolecular forces. You are fighting a network. Now, here is where Feynman would remind you not to be satisfied. Because understanding the boiling point anomaly through hydrogen bonds is not the end of the investigation. It is the beginning of a chain. Because once you understand that water has this network of extraordinarily strong connections threading through it in every direction, you have to ask what else that network does. And the answer is disturbing, because it does not do one other thing. It does everything. Every major anomaly of water has the same origin, the same hydrogen bond network. And Feynman taught that when you find a single mechanism that explains multiple apparently unrelated phenomena, you are looking at something real. You are not telling a story that fits the data. You are touching the actual structure of what is happening. So take the next anomaly, the one that is arguably the most important physical property of any substance on this planet. Ice floats. You know this. You have seen it since you were a child. You drop an ice cube into a glass, and it bobs at the surface. It seems so ordinary that you would never call it remarkable. But let me tell you what every other substance in the universe does when it freezes. It sinks. When a liquid solidifies, the molecules slow down, lose energy, and pack together more tightly. The solid is denser than the liquid. So the solid sinks in the liquid. This is not a rare behavior. It is the rule. Iron, copper, gold, nitrogen, alcohol, mercury. When they freeze, the solid sinks. Always. Everywhere. Without exception. Except water. When water freezes, it gets less dense. The ice is about 9% less dense than liquid water. 9%. That is not a tiny anomaly. That is enough to burst iron pipes. That is enough to split granite boulders. That is enough to shatter glass bottles left in freezers. That expansion is why ice floats. And the hydrogen bond network is precisely why the expansion happens. When water cools below 4 degrees Celsius on its way to freezing, the molecules slow down enough that the hydrogen bonds can force them into a very specific crystalline arrangement, a hexagonal lattice, a repeating pattern of 6-membered rings, like a honeycomb, where each molecule is held at arm's length from its neighbors by hydrogen bonds, all pointing in the right directions to maintain the crystal structure. And that lattice has holes in it, empty space in the center of each hexagonal ring. In liquid water at room temperature, where molecules are moving faster and more chaotically, some hydrogen bonds are broken at any given moment, and molecules can jostle and pack closer together, partially filling those holes. But in ice, the crystal structure locks everyone in place. The order creates space. The disorder, paradoxically, creates density. And the ice ends up lighter than the liquid below it. Now think about what this means for a lake in winter. The surface cools first because it is in contact with the cold air. If water behaved like everything else, the cool surface layer would become denser and sink. Warmer water from below would rise to take its place and cool in turn. The lake would mix. The whole body of water would cool uniformly from top to bottom, and eventually the entire lake would freeze solid. Every fish, every microorganism, every bacterium locked in a block of ice and killed. That is what would happen if water behaved like every other substance. But water does not behave like every other substance. As the surface cools toward 4 degrees, the water at the surface does get denser and does sink. But only until 4 degrees, because water reaches its maximum density at 4 degrees, and then as it cools further towards 0, it starts to get less dense again. The coldest water becomes the lightest water and stays at the surface. And when it finally freezes, the ice sits on top, because ice is lighter than the liquid below it. And that floating layer of ice, rather than sinking to the bottom, acts as an insulating lid. Ice conducts heat very poorly. The surface ice protects the liquid water underneath from the freezing air above. The fish survive. The plants survive. Life continues under the ice, waiting for spring. If water froze from the bottom up like everything else, life in temperate and polar regions would be essentially impossible. The aquatic ecosystems that have existed For billions of years, the ecosystems from which all complex life on land eventually emerged would not exist. You would not be here, not because of some improbable cosmic coincidence, because a three-atom molecule decided, by the logic of hydrogen bonds and hexagonal lattices, to expand when it solidifies. But the hydrogen bond network has more to answer for. Consider heat capacity. If you put a pot of water on a stove and try to boil it, it takes a very long time. Longer than intuition suggests for a molecule so small. The reason is that water has a bizarrely high specific heat capacity. It absorbs enormous amounts of energy without its temperature rising quickly. Iron heats up almost 10 times faster than water for the same amount of energy input. Copper is faster. Sand is faster. Virtually everything common is faster. Water soaks up heat like a sponge and barely shows it in its temperature. And the reason is, again, the hydrogen bonds. When you pour energy into liquid water, you are not just making the molecules move faster. A large portion of that energy goes into stretching, bending, and breaking the hydrogen bonds themselves rather than accelerating the molecules. And temperature is a measure of how fast the molecules move. If the energy is going into the bonds instead of into speed, the temperature barely rises. The bonds are acting as energy sponges, absorbing the heat without letting it show up as warmth. This matters at a scale that is hard to overstate. The oceans cover 70% of the planet. They are made of water. And because water has this extraordinary capacity to absorb heat without changing temperature much, the oceans act as a massive thermal buffer for the entire planet. They absorb heat during warmer periods and release it slowly during colder periods, smoothing out the temperature swings that would otherwise make the surface of the Earth almost uninhabitable for complex life. Coastal cities are warmer in winter and cooler in summer than inland cities at the same latitude, and the reason is proximity to large bodies of water acting as thermal regulators. The stability of the climate that allowed life to persist and evolve for billions of years on this planet is a direct consequence of the hydrogen bond network in liquid water. And your own body uses the same mechanism. You are about 60% water by mass. When you exercise, your muscles generate heat, a lot of it. If your body were made of a material with a normal heat capacity, that heat would accumulate so rapidly that your internal temperature would become lethal within minutes. But all that water absorbs the excess heat, keeping your temperature stable long enough for you to cool down through sweating. Which brings us to another anomaly, the heat of vaporization, which is also extraordinary, also driven by hydrogen bonds, and which is precisely why sweating works as a cooling mechanism at all. Each gram of water that evaporates from your skin carries away an enormous amount of heat, far more than you would expect from a molecule of this size, because vaporizing water means breaking the network, and breaking the network costs energy. And that energy comes from your skin, which is why you feel cool. Then there is surface tension. Water has the highest surface tension of any common liquid except mercury. Surface tension is what allows a steel needle, which is 8 times denser than water, to float on the surface if placed gently. It is what makes water form spherical droplets rather than spreading into thin films. And surface tension drives capillary action, the phenomenon where water climbs up a thin tube against gravity with no pump, no mechanical assistance, nothing but the pull of hydrogen bonds and adhesion. And that capillary action is how trees work. A giant redwood pulls water from its roots to its topmost needles, 300 feet against gravity, entirely through capillary action and the suction created by water evaporating from the leaves. There is no pump. There is no heart. There are only tiny channels in the wood, and the relentless pull of a hydrogen bond network that refuses to let its molecules go easily. If water had a normal surface tension, this would not work. Trees could not exist above a few feet in height. There would be no forests. There would be no jungle. There would be no ecosystems built around large plants. The land surface of the Earth would look utterly alien, and most of the species that depend on those ecosystems, which is most species, would never have evolved. And finally, solvency. Water dissolves more substances than almost any other common liquid. It is sometimes called the universal solvent. And again, the reason is the dipole, the permanent electrical imbalance that drives everything else. Those slightly positive hydrogen ends and slightly negative oxygen ends of water, molecules can surround ionic compounds, like the sodium and chloride in table salt, and pull the ions away from each other and keep them separated in solution. The attraction between a water molecule's dipole and a dissolved ion is strong enough to overcome the crystal forces holding the solid together. And this means that the chemistry inside your cells, every enzymatic reaction, every signal transmission, every nutrient transport across every membrane in your body happens in a medium that can dissolve and carry an extraordinary variety of molecules simultaneously. Without water's ability to dissolve what it dissolves, the biochemistry of life as it exists would simply not function. So let us take stock of what we have. Water has a boiling point that is 180 degrees higher than it should be. Its solid form is less dense than its liquid form, which is the opposite of almost every other substance. It has an abnormally high heat capacity, an abnormally high heat of vaporization, an abnormally high surface tension. It is an abnormally effective solvent. 6 anomalies, 6 violations of what you would predict from a molecule of this size and weight. And every single one traces back to the same mechanism, hydrogen bonds, which trace back to the molecular dipole, which traces back to the geometry of the molecule and the electronegativity of the oxygen atom. 1 mechanism, 6 consequences, each one essential for the existence of life on this planet. Feynman would say that when you find something like this, when one underlying structure generates multiple, seemingly independent phenomena at completely different scales, you are not just learning a fact about chemistry. You are learning something about how nature works. Nature does not construct elaborate, separate explanations for each thing it does. It finds a single mechanism and follows its consequences wherever they lead. And the consequences of the hydrogen bond lead all the way from the molecular scale, where protons and electrons interact over distances measured in angstroms, to the planetary scale, where climate is regulated over timescales measured in millions of years. But Feynman was also a man who valued intellectual honesty above almost anything else. And honesty requires acknowledging what we do not yet fully understand. And there is a version of this story that would be dishonest if I left it at the clean summary of hydrogen bonds explaining everything, because the details of water's behavior at the molecular level are, even now, not completely resolved. The structure of liquid water at room temperature, specifically the way hydrogen bonds organize and reorganize themselves continuously as molecules move, is still being studied with experimental and computational tools that Feynman himself did not have access to. There are physicists and chemists who have spent their entire careers on this question and will tell you plainly that there is still genuine uncertainty about the microscopic details. There is, for instance, the Mpemba effect. A Tanzanian schoolboy named Erasto Mpemba noticed in the 1960s that his hot ice cream mixture froze before his classmates' cooled mixtures. His teacher dismissed him, but when a physicist named Dennis Osborne visited his school, Mpemba asked again, and Osborne went back to his laboratory and tested it. And sometimes the hot water did freeze first. The effect has been reproduced. It has also failed to reproduce under carefully controlled conditions. And there is an explanation involving hydrogen bonds specifically, the idea that hot water has a differently structured hydrogen bond network than cold water, and that some of those configurations nucleate ice crystals more effectively, allowing the hot water to take a shortcut to freezing that the cold water cannot take. A glass of water, in a sense, remembers where it has been, not mystically, but physically, in the arrangement of its hydrogen bonds. This is not settled science. This is an open question. And that water, the substance you drank this morning, can still generate open questions in serious scientific literature in the 21st century, is itself something that Feynman would have found deeply satisfying. And then there are the quantum effects. because Feynman taught physics at the level where quantum mechanics is not a curiosity but a necessity, and water has quantum secrets that most descriptions never reach. The hydrogen bond involves a proton, the nucleus of a hydrogen atom, sitting between two oxygen atoms with a small energy barrier separating its native position from the neighboring oxygen. Classically, the proton should stay where it belongs. It does not have enough energy to climb over that barrier, but protons are light. And quantum mechanics tells us that light particles are also waves, and waves can pass through a barrier without ever having the energy to go over the top. This is quantum tunneling. And protons, barely massive enough for quantum mechanics to get a grip, tunnel through the hydrogen bond barrier in water, flickering from one side to the other in ways that classical physics says should not happen. In ice, it gets stranger still. In rings of 6 water molecules, the basic structural unit of ice's hexagonal lattice, all 6 protons can tunnel simultaneously, switching positions in a coordinated quantum motion. Not one, then the next. All 6 at once. Because if a single proton tunneled alone, it would violate the local constraints on how many protons can be near each oxygen atom. But if all 6 tunnel together, those constraints are satisfied everywhere simultaneously. So the quantum event is collectively enforced by the crystal structure. This is a macroscopic quantum phenomenon related in its mathematical structure to the same mechanism that produces superconductivity in certain metals. Not in a way that makes water a superconductor. But the underlying quantum trick, collective behavior enforced by structure, is the same. What does all of this add up to? It adds up to the argument that Feynman would have structured in this exact way. You begin with a concrete anomaly. You identify the microscopic mechanism responsible. You follow the consequences of that mechanism until they show up as macroscopic properties at completely different scales. And you arrive at the understanding that a 3-atom molecule made of 2 of the most common elements in the universe is, in its combination of anomalous properties, utterly unique, not 1 or 2 anomalies. The full package, the density inversion, the extreme boiling point, the extraordinary heat capacity, the heat of vaporization, the surface tension, the solvent properties, the quantum tunneling, all of it from hydrogen bonds, all of the hydrogen bonds from a molecular geometry, all of the molecular geometry from the angle at which oxygen and hydrogen combine, and from the electronegativity that drives electrons toward one side. No other known substance combines these properties. Ammonia has been proposed as an alternative solvent for life elsewhere in the universe. Liquid methane exists on Saturn's moon Titan and has been considered. But neither of them provides the full combination. Neither of them does what water does. And when astronomers look for life on other worlds, the first question they ask is whether liquid water is present. Not because we lack imagination about what life might be, because no other known substance provides all of these functions simultaneously. Water is, as far as we can tell, alone in what it does. And this is where Feynman would want to be honest about the deepest question. Because you could look at all of this and say it seems too perfect. It seems like these properties were designed for life. And Feynman was clear about how to engage with that impulse honestly. We do not know why the fundamental constants of nature have the values they have. We do not know why the charge of the electron is what it is, or why the electromagnetic force has the strength it does, or why the periodic table has the structure it has. We can say that the laws are what they are. And one consequence of those laws is this molecule. And one consequence of this molecule is us. Whether there is a deeper reason behind the constants, that question stands at the frontier where physics gives honest answers by saying it does not yet know. And Feynman said that acknowledging that frontier honestly, rather than dressing up ignorance as understanding, is the correct intellectual attitude. So what does this leave you with? Not a collection of facts about a liquid, not a chemistry lesson. What it leaves you with is the experience that Feynman said physics offers repeatedly to anyone willing to examine things with sufficient rigor. The discovery that the world is far richer than any initial intuition suggests. that the substance you drank this morning, the substance you have handled every day of your life without questioning it, the substance so familiar that its name barely registers as interesting, is not simple in any sense that matters. It is a physical system of extraordinary depth whose properties emerge from a single molecular feature, cascade across scales from the angstrom to the planetary, and still hold open questions that serious researchers are actively working on right now. Feynman made a distinction that he returned to throughout his life, a distinction between knowing the name of something and understanding it. He said that there is a difference between knowing that a bird is called a brown-throated thrush and knowing what the bird actually is, how it lives, how it moves, what it does, and why. And he said that familiarity with names without understanding of mechanisms is not just incomplete knowledge. It is a specific kind of blindness. You see the label and mistake it for the thing. Water is the most striking example of that blindness in ordinary life, because almost everyone knows the formula. Almost everyone knows the basic facts. And almost no one, until they follow the argument that Feynman taught, understands what water actually is, what they are drinking when they drink it, what the anomaly is, where it comes from, and how many other things that anomaly makes possible, including the fact of being alive to drink it at all. The substance you drank this morning should have been a gas. It was not. Every single thing that makes your life possible, and everyone else's life, and every ecosystem on this planet depends on the fact that it was not. And the reason it was not is a 104-degree angle in a 3-atom molecule, and the electronegativity of an oxygen nucleus. That is the chain. That is what Feynman meant by following the argument where it leads. That is what it means to understand something instead of just knowing its name. And now, every time you look at a glass of water, you should feel something you probably never felt before when looking at water. Not wonder in a vague and sentimental sense, but the specific, clear, almost vertiginous recognition that the most ordinary thing in your world is, if you look at it honestly, one of the strangest things that exists.